ungrounded three-phase systems. In this presentation, we're going to be looking at where are ungrounded systems, challenges with ungrounded systems, solutions for ungrounded systems, as well as the three-lamp method, zigzag transformers, and using CTs for alarms. Standard Delta three-wire sources are ungrounded. Now, services of this design are no longer provided, but there are still some systems in use today. This example here, you can see that there are only 3 conductors coming in, and it's off of a system that is ungrounded. Other sources that are not utility provided also are ungrounded. When three-phase electrical energy is generated, it's typically accomplished with three-phase three-wire, or delta no neutral. In a situation like this, we are again dealing with an ungrounded three-phase source. At other times, we have separately derived delta three-phase sources that are utilized when we have to provide different voltages at a facility. Let's say we have a building that's 120/208 three-phase four-wire, but the rooftop equipment is 600-volt three-phase three-wire. Well, we can use a transformer 208 to 600, and most likely what we're going to have is a delta to delta. There's no need for us to run a neutral up to the roof because there's no connection for it. So in this case, the secondary being an ungrounded separately derived system, how do we deal with that? And what challenges might we encounter? Now, under normal operation, there's a near zero voltage between any line conductor and ground. Line to ground shock potential for personnel is almost eliminated entirely, and most of the older electrical systems utilize this type of form, ungrounded. Solid ground faults cause a rise in the voltage from the unaffected line conductors to ground to the full line voltage. So if we have a solid ground fault from this conductor to ground, it means that now the voltage between these conductors and ground, the two unaffected lines, has risen to 480 volts. Now, no breakers trip, and that's because there's very, very little current that will flow from the ungrounded conductors to earth. Since it's so low, there's no overcurrent that's going to operate. Now, all electrical loads can continue to operate normally without the risk of an uncontrolled shutdown due to the automatic operation of an overcurrent. And this is seen as a good thing. In industrial environments where an unplanned shutdown could cause catastrophic failures of different types of process controls, it's optimal if we don't have to shut everything down. Now, as we said before, we typically have a very little voltage that is measured between these conductors and earth. But to add a little bit of confusion to the whole discussion, all electrical systems are capacitively coupled to ground. The EMF of the system voltage combined with the insulation of the conductors creates a natural capacitive effect that cannot be eliminated. And what this means is that there's an extremely small current and a varying voltage potential between each conductor and earth during normal operational conditions. So kind of weird. But this has some really large ramifications when we start having ground faults. So most ground faults in the industry are not solid, but instead they're arcing. And arcing ground faults cause heat, damage, fire, and extreme voltage disturbances in ungrounded systems. Under normal conditions, the voltages to ground are equalized and fairly minimal because of that capacitive coupling. But as soon as we have an arcing ground fault, you don't have to memorize this and you don't have to know everything that's happening on this page, but just believe by looking at where that funny little Y system is, that the voltages are getting extremely excessively out of balance. So a very high voltage spike, and it's not even consistent, will start to take hold. So 480 volts, upwards of, 1200 volts. What this will do is start causing insulation failure through the conductors, as well as any equipment that has fairly light or minimal insulation, most predominantly motors. So motor windings will start to fail on a regular basis. Motors will start going offline. Every week we're replacing one or two motors. Why is this happening? It's because of an arcing ground fault on an ungrounded system. Now, just like in a solidly grounded system, if two ground faults were to occur, of course, we're going to have a line-to-line short circuit and extremely high fault current will flow between the two line conductors and earth. There's a possibility of, arc blast, arc flash, damage to equipment, personnel injury before the overcurrents can open the circuit. And of course, the two overcurrents would open the circuit because of the high value of current flowing. Now, when a ground fault occurs, there's no way to determine which line has faulted or where in the system the fault is. The search could be a long time intensive process that could take days. The longer the ground fault goes unrepaired, the higher likelihood there is of insulation damage or a full line-to-line short circuit. And so because of that, we need to have some additional tools built into the system to assist. There are two main solutions. One of them is a ground fault detection system. The other is an artificial grounding system. Let's look at the ground fault detection system first. In its most basic form, a ground fault detection system is known as the three-lamp method or three-lamp installation. It is simply three lamps that have a fairly high voltage rating, and they are connected together in a star formation or Y at one point and then grounded. Now, on a 480 volt system, each of these lamps is rated 480 volts. And under normal conditions, the three lamps will be dimly illuminated, and that's because they're connected in Y, and because of that, the phase voltage of 480 in Y would be 277 volts, so dimly illuminated because they're rated for 480. When a ground fault occurs, the voltage measured from the grounded line to earth drops to 0 volts. And that's because we have a connection between those 2 points. And what this means is that the lamp connected to the affected line will go dark. And that's because there's 0 volts across it. The voltage measured from the two ungrounded lines to earth rises to the full system line voltage. So in this case, it'd be 480 volts. This causes the two remaining lights to increase in brightness as they are now connected in parallel across a 480 volt source. So it becomes immediately apparent which line conductor has a ground fault, and it's illuminating, so it makes it really obvious to the individual. Now, the three-lamp ground fault detection system is cheap. It detects ground faults, assists in locating ground faults. It does not prevent damage from ground faults, does not prevent line-to-line short circuits, and it kind of requires that someone must always be watching the lamps. Another option is a Zigzag three-phase auto transformer, also known as a zero-sequence transformer. Now, a Zigzag transformer is a very specialized type of auto transformer that has no secondary winding. There are 4 connection terminals, H1, 2, 3, and HO. HO connects to a resistor and then to ground. The purpose of using a transformer like this is to reduce harmonics, eliminate voltage spikes in ungrounded systems, and it's very commonly used for this for wind generation grounding. This is what it looks like. You've got a large resistor, and the Zigzag transformer is the item on the right-hand side of the cabinet. Now, the way that they accomplish this, there's no electrical isolation from primary to secondary windings, and its purpose is to provide a common connection to all lines of an ungrounded system. It accomplishes this by winding a single wire from primary to secondary on a different phase and an opposite turn direction. So if we follow this A conductor, we can see the direction it's wound, and then the same conductor goes to the middle leg and is wound in the opposite direction. This is by no means something you have to memorize. Instead, you must know what a zigzag transformer is used for. When a ground fault occurs, the zigzag transformer provides a path for current to flow back to the ungrounded system. This has two advantages. Well, actually, there's three here. Voltage to ground does not rise during the fault. The voltage spikes are reduced, and overcurrents will operate because current will be flowing to ground. So typically, we have a very large resistor that is then connected in series with the zigzag transformer. So here is a full installation. We have a ground fault. Current flows back to the system through the zigzag transformer, and we can put larger resistance values in there to limit the fault current. So the zigzag artificial grounding system detects the ground faults, assists in locating ground faults, prevents damage from ground faults, does not prevent line-to-line short circuits, but really nothing does. And other than a breaker tripping, there's no audio-visual to alert personnel of a ground fault event. So that's seen as kind of a downside, right? We still don't know if this is happening. And so to our rescue comes the use for a CT. By using a large window CT, the secondary current developed by residual flux, as in when there is unbalanced current or current flowing that is not going through the window of the CT, will trigger a visual or auditory alarm like this. We can use this in addition to an artificial ground or in addition to a 3-lamp system. So commonly you'd see something like this or something like this.